All right. As some of you know, there was a posting of possibly the idea that we might not be here today, so we put a little presentation or a little video together on what our next segment is. And you were handed out 3 different types of problem-solving papers. Whether you decide to work on the first one today, that's entirely up to yourself, because the reason that we had done that is some students will be gone today and tomorrow as well. So we continue our segment on dealing with gases. And what, for instance, do those 2 problems have in common that you see? What do you see? They're both measured at temperature and same temperature, standard temperature and pressure, not same, standard temp and pressure. And we had learned that last, well, I'll call it section. The standard temperature is what? 273 degrees Kelvin. The standard pressure is what? 1 atmosphere. Now, one of the things that you'll notice, there's a progression on this problem solving. That worksheet 1 deals with calculating moles and masses of gases when they're all measured at STP. Okay? So the best way to do these problems is with dimensional analysis. And how we go about and make that determination can be found then, or an explanation for this if you want to call it that. 380. 380. I know I got 382, but we'll be making a reference to that here shortly. Okay. Where we see molar volume of a gas on page 380. Okay. What goes on to talk about is, recall that 1 mole of a molecular substance contains a number of molecules. And if we're talking about Avogadro's number, that is what without looking? That is correct, okay? And equal to Avogadro's constant, 6.022 times 10 to the 23rd molecules per mole. And again, that's just a counting unit. And the best way that we had described on what these counting units are, for instance, someone might say this desk is 96 inches wide. But what's a more simpler way of saying it's 8 feet? Again, that 8 is just a counting unit, accounting for the number of inches per foot. So, with this, 1 mole of oxygen contains 6.022 times 10 to the 23rd diatomic oxygen molecules. And one of the things, when you see that oxygen, you've got to wrap your head around this. We've said it about 3 or 4 or 5 times now. When it comes to these gases and halogens, what's true about that? Someone need a pencil, because I see you grabbing one and going like this. And, all right. Yes, they're diatomic. So that's why it says O2 rather than just oxygen there on page 380. Okay? We haven't got to the more important aspect of it yet. So when we're looking at the atomic mass, it says 31.9988, which we can safely round up to 32 for our purposes. Okay? So 1 mole of helium, a monoatomic gas, contains the same number of helium atoms and has a mass of 4.00. Okay? Notice we're not doubling the helium because it is not diatomic. Okay. And I probably would have gone into this yesterday had I remembered the textbook, but I left it up here and I wasn't about to go running home or running up here for that. Okay. So now we're getting to the important information. Okay. According to Avogadro's law, 1 mole of any gas will occupy the same volume as 1 mole of any other gas, same temperature and pressure, despite mass differences. The volume occupied by 1 mole of a gas at standard temperature and pressure is known as the standard molar volume of a gas. It has been found that 22.4, that's another constant that you're going to want to get to remember. So for every 1 mole of a gas measured at STP is 22.4 liters. Okay. So, knowing the volume of a gas, you can use 1 mole per 22.4 liters as a conversion factor to find the number of moles and therefore the mass of a given volume of a gas at STP. You can also use the molar volume of a gas to find the volume at STP of a known number of moles or a known mass of a gas. Okay? So in this progression, this first paper just deals with calculating moles or maybe masses of gases when they're measured at STP. Now, when you get further into that of the second paper, not all gases will be measured at STP. So, well, there must be a way that we can calculate that, and there is. What was our abbreviated form of making reference to the combined gas law? What did we call it? SIGL. That's right. CGL or SIGL. Then, when we get to where we're measuring gases that are not measured at STP, we call it IGL, then IGL. And that refers to the ideal gas law, and we'll get to that at a later time. So you would be able to see that on top of page 383. That will be coming next. And one of the references that we make, and here's another constant to remember besides 22.4, and that is the constant found on page 384. And it's the second one down on table 2. Okay? What's the numerical value for R on table 2, the second row down, not column? 0.0821. That is a constant that we want you to be able to memorize as well. When it'll make more sense when you look at what they're measured at. What's the measurement for that 0.0821? What's the unit for pressure? Atmospheres. What's the unit for volume? And then also degrees Kelvin, and that's per mole. And that's why we use that constant. Okay? So if you divide, I'm guessing, 22.4 by 273, let's just find out. Okay? 22.4 divided by 273, and what do you know? 0.08205, which they round up to 0.21. That's where that number comes from, because again, not all gases are measured at STP, but believe me, this is your friend here. When we're talking about these types of problems. Okay, so before we get to the book examples on page 382, we're looking at, for instance, how many moles of hydrogen are found in 785 milliliters at STP. Now, one of the things we talked about in yesterday's presentation is when we look at this volume, what do you suppose you have to have that in? Has to be in liters. You can show that mathematically, or you can just make that conversion in your head. And how many of you think that that just sounds terrible, converting that in your head? Good, because what do you do to change it to liters? Sure? You're sure? No. You were right the first time. 1,000. Yes, or you can just show it by doing what to this decimal. Here's the decimal point. Right? Right? Right. Right. Right or left? Right. Right. Kind of reminds you of who's that, Abbott Costello? Who's on first? What's on second? I don't know who's on third. Never heard that before? Yeah. So you say, move it to the left, I say, right. Yeah. Just seeing if you people are awake. Are you awake? Well, we're chewing gum, so we should be. Yeah. Okay. So what we do here is, again, this is just the best way to do this is just dimensional analysis. And so if we take 0.785 liters now, okay, you can put that step in if you wanted to, 785 milliliters, and what you're doing is that for every 1,000 milliliters, you get 1 liter. So you're dividing by that 1,000 and moving it to the left, correct or right, okay? So that's why I put correct in there. So that's how you get 0.785 liters now. So what are we ultimately looking for in this moles? So there's a specific conversion that we can use as presumption for converting a volume of a gas to a number of moles of a gas when it's measured at STP only. And we told you it's one you're going to want to memorize. It's not 0.0821 either. 22.4. Now, that's how many liters are in 1 mole of any known gas when it's measured at STP. So, just like we've been doing for a long time, here's that dimensional analysis that we've been utilizing since last fall. So, how do we get liters to cancel out then? Okay, correct. Well, someone's trying in here. Are you two just tagging along for the ride? All right. And I understand this is new material, though. This is brand new material. But one of the things, what did we say about general stoichiometry or reaction stoichiometry? It may knock you down, which maybe some of you said it did. But what does gas stoichiometry do to you? It might finish you off if you don't get up again. Okay? So, what we see happening is we want to make this conversion of 22.4 liters of any gas measured at STP gives you a mole of that gas. Now, one of the things, now be careful, now this is just going to be human nature. If we said how many grams of hydrogen are found in here, we could do that because once you have something measured in moles, you can convert it to grams, right? Okay, so the answer here would be dividing 0.785 divided by 22.4, and that would give you your moles. Just like back in chapter 3 then, we would say, well, if you have, I don't know, 0.035, is that right? 0.035 moles of this substance then, well, how would you convert that to grams? Well, you don't have to do this in a multi-step problem. Now, here's where people will make mistakes. What do we say about mistakes? 2 things. Well, try not to repeat them and try to learn from them. You're going to make mistakes once you leave high school, once you get out on your own, once you're in college. Yes, we're going to make mistakes, but let's try to learn from them and try not to repeat them. Okay, so what would we do to convert this to, instead of how many moles, if we wanted grams? So for every mole of hydrogen, how many grams do we have? Sure? Okay. What is hydrogen? It's a gas.
So 2.02.
Because, again, some people don't want to put these labels in here, but if you always carry that and you put that 2 behind there, now you know it's 2.02. And again, that's just human nature to do that. So what may happen is some people will either have half as much as what they need or should have twice as much as what was needed. And that's because we inadvertently or mistakenly forget that gases and halogens are diatomic. Okay, so, but in this problem, you had correctly said 0.035 or whatever that was, because we're just looking for moles, not grams. Okay, left side, are we good? Right side. Okay, so then what about if we're looking for a volume where we're given a number of moles then? Okay, so when we're talking about methane or CH4, which really doesn't have anything to do with the problem, because we're not looking for what of that gas. I mean, it doesn't really, it's not necessary to know the formula for methane because we're not looking for the what? Up there I see it. We're not looking for the mass of it. I didn't know whether the loop moved left or right, but I see the reflection off the camera. Up, yep, there it is. Okay. So in this case, again, there's only one place to start. That is 3.14. 3.14 moles, but we're going to just attach that label just for good practice. Moles of CH4. Okay? So, how do we convert this to a volume? Because it's asking for milliliters. So for every mole of methane, okay, 22.4 liters now, and I would suggest, until you get a really good understanding of this, okay, that you put this step in here, but really you could say, what, 22,400 milliliters? Okay, because if we had 22.4, and that's in liters, we would change that to 2024. Okay, so there's one, and then two more. So 22,400 milliliters. It's the same thing, but I would suggest, until you get a really thorough understanding of this, that we go ahead and put that liter down here and 1,000 milliliters up above. Okay. Once you get better at this, you're going to be able to recognize that, oh, if this gas is measured at STP, we know that that's 22,400 milliliters rather than just saying 22.4 every time. But until you're able to do that, I would highly suggest that you put that extra step in there. Just like the same thing when it comes to solving for whether it's speed / velocity. Do you remember what that formula is from physical science? Velocity equals okay? So when you're given that equation, or if it's a density problem, one of the things we say, don't try to memorize 3 different formulas, okay? Because if you're solving for the velocity and you have these two, okay, that's fine. But if you have the velocity and you have the distance, you need to solve for the time, don't try to memorize 3 different formulas. Just use one universal formula and continue from there. All right, so we're on the bus so far. Yes. So left side's good. What about the right side? All right, so we'll go ahead and erase this. So now we'll go ahead and look at page 382. Okay. All right, so on page 382, it's got some sample problems on there you could work with, but for instance, we see the practice problem. Assuming all volume measurements are the same temperature and pressure, but I like to say standard temperature and pressure makes more sense, what volume of hydrogen gas is needed to react completely with 4.55 liters of oxygen gas to produce water vapor? Now, we're not worried about the water vapor. We just want to know, okay, what volume of hydrogen gas is needed to react completely. All right. So, ooh, is this, that might be gas stoichiometry. That might be getting a little ahead of ourselves. I don't think we want to do that yet. That is a chemical reaction that we would need. I'm sorry, back up to page 381. We're not ready for putting a chemical reaction and changing the hydrogen into water vapor. Okay, so practice problem number 1 on page 381. At STP, what is the volume of 7.08 moles of nitrogen gas? You want to work on that yourselves? Or, okay, so again, I get to kind of take a shortcut. Okay. And then we'll go ahead and come back to that. Again, see, my book gives the answers, but what good does that do if you don't know how to get there? It's kind of like, well, it doesn't show you how to do it either. So, so for instance, it's like, oh, how do you get to Arlington? You know, the practice problem, it does show you how to do it. Oh, I didn't think they showed you the practice problems.
No, the sample problem.
Sample problems, yes, not practice. Did I say sample? I meant practice. Oh, okay. All right. Okay, we get 159. Okay, well, so 7.08. Now again, it doesn't matter whether you have the label in there, but just for good practice, we're going to put N what? Because it's diatomic, okay? So, what we see happening is for every mole of a gas measured at STP, it's how many liters? So for every mole of nitrogen at STP, we get 22.4 liters of nitrogen at STP. So we go ahead and multiply them out. 7.08 times 22.4. And yes, you get 158.59, which they say round up to 159. Liters. Okay. Now, again, there may be some changes you have to make for those of you who want to take this in college when you're using significant figures. What they're saying here is 3 is the proper number of significant figures, so that's why the book gives it as 159 instead of 158.59. But for our purposes at this point, we're going to say 158.59. Okay.
So what we just did, like the first problem, that's our worksheet.
That is correct, except for the 10th problem. I think the 10th one's kind of a review.
How many moles?
Maybe it isn't, but I was thinking that it was. Oh, it is. Oh, okay. Maybe it's the ideal gas law worksheet. Maybe as a review then. Okay, fair enough. Oh, okay, yeah, the double replacement reaction. See if you remember that from last semester. That we will see, that's right. Okay, so do you want to do another practice problem? Now, what would happen, what about, how would we find the volume of nitrogen measured at STP if we had, give me a number between 5 and 600.
123. Yeah, 5 to 600.
So between 500, 523. Okay? So if we had 526 grams, now, again, human nature, where are people going to make a mistake here? Well, one thing, okay, let's say they did do that, but we made reference to this last semester. Some of you may be working diligently at home and all of a sudden, beep, 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 beep. Oh, I just got a Snapchat. I better check this Snapchat out. Are we laughing because I'm sounding funny doing that, or are we laughing because it's true? Or both?
A lot of adults usually go snap face, and it's called depression syndrome.
Oh, okay. Yeah. I don't Snapchat. Okay? So, what people may do is, how are we going to get from grams to a volume of a gas measured at STP?
You have to do.
We need to get rid of that gram.
So you have to do
Grams up.
2.4.
You got the right idea. No, because we've got a mass here. You're trying to do this in the mole conversion. We're not that far yet. You got the right idea, but you're too far ahead of yourself. So we got to get this to moles. How do we do that?
So you have to divide by 20. Nitrogen is 14.
Well, don't multiply it on your calculator. Just double 14.
28.02
Okay?
is 1 mole.
But why may people put 14 here?
Because they don't have it diatomic.
Or, oh, they just got a Snapchat.
No.
Me doing my homework. You got such a smile face on. Yay! Okay, so we cancel this out. We got 28.02 grams of nitrogen, and that gives you one what? A mole of nitrogen. Now we're on the home step. Now how do we get to volume?
So you have 1 mole on the bottom, and then you have 22 point.
Don't say it like a question. Then you'd have it done, yes. So it's no surprise.
So you're mixing some stuff that we did like last time. Okay.
Yes. And then when we get the furthest along in this chapter, like that problem that I read, we're not quite ready for that yet. Where it's talking about reacting hydrogen with oxygen to give water vapor. That's gas stoichiometry. There you need a balanced chemical reaction. We're not quite ready for that yet. Okay, so once we do get to that point, the gas stoichiometry, that's worksheet 3, you need to decide, am I a dimensional analysis person or am I an ideal gas law person? They work for both cases, but if you're given an amount of a substance in grams, you're going to have to use dimensional analysis to convert to moles anyway. But again, we're not that far yet. So with this, the big thing to remember is this guy right here, because it's measured at STP. So you can use 22.4 liters for every mole of that substance, as long as it's a known substance, okay? But if it's an unknown gas, so then you'd probably have to use the ideal gas law. But again, that's the second paper, not the first. So each and every one of them problems, okay, is solved in this manner. There was a presentation that was put together for you yesterday, so I'll leave you that time. It was only like 15 minutes, and a lot of it says about the same thing. But are we good with this information here? Okay, so barring no questions, I'll leave you for to work on this. Work on it, don't work on it. I'm not formally assigning it today. I will tomorrow, and then that will be due then on Thursday. Now, I guess I don't need to have this recording for this conversation about the weather. So that can be dealt with at a later time. Okay, we'll pick up with you next time.